introduce you to a charity I'm involved with. There's a 5K run coming up on October 5th. It's a Saturday morning. So when I was a grad student, I used to run about just a couple of miles just around here, the Charles, and then somehow I got more into it. And apparently 28 is the age you're the best for running. So I passed that, but I was still able to run a marathon last year. And I think it's great. It's great for relieving stress and all that. So anyway, it's not so much for fundraising. We need people either to volunteer to, keep track of the runners. It's going along the Charles River just by Harvard Square, but on the Boston side. So it's Saturday, October 5th. What I'll do is I'll put it there. That charity essentially built a school in Guatemala. What happens there is there's a lot of inequality. So the poor are really, really poor. And they bring students that instead of going to school would just go to the dump to recycle stuff. So it's pretty serious, the condition of living there. I'm not going to say it's the only situation where it's really bad. There are a lot of bad things throughout the globe, but I think that they essentially are nationwide, and they try to raise $1 or $2 million a year to sustain the school. There are a lot of donors that are retired people and all of that. So there's actually more money right now than runners. So if anybody is interested, either to volunteer or come, it'd be great. And if I find enough, I can do the shuttle from the campus or something. That would be something I'd be really happy to do. So think about it. It gives you 2 or 3 weeks. All you need to do is be able to run 2 miles right now. If you can't run 2 miles, maybe you can walk it too. So registration at 8. There's walking run at 8:30, and the real running is at 9. So if you want to beat me up, you need to come at 9. The idea behind so I'm on whenever. The idea behind the dump stuff that they're doing, they really go and pick metals, and they pick anything that they can resell for a value. And it sounds terrible, but I just happen to be aware of a little bit how the recycling works for materials. So residential recycling, when there's like this single stream recycling, it gets to China as a container. So that's after 3 or 4 weeks, if not sometime more than a month of collection. So it's not the cleanest business that you can think of, and they have manual ways and automated way down there, but essentially we outsource the residential recycling of materials. So if you or your family have the opportunity to still go to a transfer station and sort it through, from my perspective, it's better because it doesn't go through this aging process and transportation and all that. But it's the reason they do it that way is just economics, and I know that's what Professor Eger is covering in this part of the class. But so there are good things about recycling, but the single stream is more or less they could label it as offshoring of recycling because they don't want to deal with it anymore. Today we're going to continue on this processing overview, and one advantage of this class that comes with working with Professor Eger is we have flexibility. As you can see, we sort of change days, who's teaching when and what. And in terms of topic also, we cover such a broad topic that I started with you guys on processing at the first week of class, and I realize now that 4 hours is not going to make it. So I'm planning to do 6 hours on that processing overview, and that will be considered a half module. And then we will talk about material behavior still in the second part, but that's also going to be a 6 hour. So that's just a little change, and it will make it a little different, I guess, but some of these 12 units were already broken down in very different things. So I think that may be a good thing in the future. People know, is this really going to be material selection or it's going to be non-destructive testing, which are, different things. So we'll talk today, and I do want to always come up with a little summary from the previous lecture because I know you guys don't have exam. You're not going to come to me, in a month, say, what should I read, for the exam tomorrow. So I've learned that it's good for me to give you a little bit of what happened last time. So last time we talked about casting, and I mentioned about sand casting as being a very cheap process. It allows you to get the special shape, and we have this complex fitting here. You get the marking, you get the little arrow, and you see the finish. The finish is a little rough because of the mold geometry. It's cooling slowly. It's used for cast iron that you can have as a regular cast iron or a ductile iron that we talked about. And then I mentioned that for assembly purposes, for fit up, they machine the flanges here to make sure that they get exactly square pieces for making mechanical assemblies. We talked about the investment casting, where you build up that wax mold and you're really going to lose it down the road. Every time you have to build that new geometry again, and that's where the investment work come from, or the lost wax casting. We talked about aluminum wheels, the die casting process. And we talked about a variation where instead of having this solidification structure with the dendrites, you can have more of an homogeneous and deformable structure. So these are options that you can generate by working at a temperature between the beginning of the solidification and the final stage of solidification. And we went through that in good details as far as segregation and why even the phase diagram tells us that we're not going to solidify all at once, that we will have these. Most of the time it's an issue. If we could avoid, this segregation and all that, I think in general we'll be happier. Now, because we can't avoid it, we work the metal, and I talked about that just a little bit last time. Today, that's our focus. We're talking about taking the cast billet, the big broom or whatever it is. It can be a square this big, and reduce it to, make a bolt, make a tube. And I've got a few examples here. This is deceptive. So I'm going to circulate that one around, and I want you guys before the end of the, be careful, it's heavy. I want you guys before the end of the class to tell me how you think it was made. It's probably means something, but I think it's useful for you, and we have different backgrounds in the class, but what I want to do is just introduce deformation before talking about deformation processing. So the elasticity is important. In stretch forming and all sorts of forming operations, you get spring back of the metal because of the elasticity. On the other hand, what we make use of in deformation processing is the plasticity, the movement of dislocation that allows you to get very high strain ratios in the material. So I want here to just draw very briefly the difference. In elasticity, we stretch the bonds, literally, between the atoms. In plasticity, we move dislocations for most of it at ambient temperature. There are other processes. You can have grain boundary slidings, a number of other processes, or just even diffusion will lead you to permanent deformation. Yes? Oh, thank you. That should be easy to fix. PC1. All right, that was the problem. Thank you so much. You should all have the handout as well. If you don't, we have multiple copies. Today we have more copies, I think, than we need. So the summary I was presenting to you is this idea that in plasticity, because you're moving dislocations, because you need to have relative movement inside the crystal, it's rate dependent. It doesn't happen instantaneously. If all you want to do is stretch bonds, it's acting like a spring. But when you want to coordinate the movement of the dislocations, it becomes time and temperature dependent. And that's why we do high temperature processing, because we want to make sure there's enough movement of dislocation so we don't damage the material as we're deforming it. We can get a lot more strain in the material without inducing damage at high temperature. And the other thing that I mentioned briefly last time, at high temperature we get more diffusion. So we get to eliminate a good proportion of the segregation issue by being hot enough and diffusing between the core and the surface of the workpiece to homogenize, and that's what it's called, homogenization of temperature. Now, the one slide about elasticity, which the reason I do this is I remember when I saw this slide, it helped me for a long time. And I've learned engineers, if you graduate with a bachelor degree from any good school in the US, you're likely to make some of the mistakes because you forgot about some of this. What I want to emphasize with the elasticity is it's the competition between attractive forces and repulsive forces between the atoms. And it's unbalanced. What you can see here is the repulsive forces goes to very, very, very high here as opposed to the attractive force. And that makes the whole potential curve non-symmetric. The fact that it's unsymmetric, you can just use this here to explain why the metals are going to expand with temperature, because as you increase the temperature from that low energy point here, the average between the two curves goes to your right here. So if you have more thermal activation, you're willing to move like this, but then your average distance between the atoms going up. So you can use this as a simple exercise to understand there are more consequences in trying to bring the atoms together than to spread them apart. And that also explains Poisson's ratio. If you pull on a material in a tensile test, you get an elongation in this way, and you get lesser of a contraction in the other way, because what it means in the contraction is all of a sudden the bond distance is going down, and the material doesn't want to do that as much that it's willing to go to a greater distance. So that's why essentially in elasticity the volume increases. These are some typical Poisson's ratio. So if it was exactly incompressible or not, essentially with no volume variation, all these Poisson's ratio would be 0.5, and you can see that they're all less than that. So there is expansion going on when you have multi-axial loading. This is the analogy I used before with engineers. I don't think you need it. I think that the example, the real explanation is that potential curve here with respect to why we get more extension in elasticity. So our focus, again, is plasticity for this class. It means that we go beyond stretching the bonds. We start having the movement of dislocation, they multiply, and I wish I could give you a 6-hour probably on dislocation, but I don't think everybody will appreciate it. So I'm thinking about talking about it a little bit because it helps explaining some of the hardening mechanisms. So we're going to cover a little bit in the next class, the more dislocation details. For now, we're going to deal with the materials at the microscopic level. So if I take this bolt, what will happen if I pull on it, it will deform and keep its shape because it's hardening. And then eventually, the metal inside all of this is going to start tapering down in terms of hardening rate. And that's where you get your instability. If you're dealing with a rubber, the instability will take a very long time to come up because the rubber will keep getting stronger and stronger as you pull on it. The metal, at some point, it gets saturated with all the dislocation, and therefore it will, you can see here the curve is going down. You have less hardening as you keep pulling on it. And eventually, you form that neck, and the deformation localizes. One thing that especially structural engineers, mechanical engineers have a hard time understanding is the metal doesn't get any softer. It's not because you see the peak here that it means that all of a sudden you have softening of the metal. What happens really is because the deformation is localized here, you have a reduced area. So if you correct this plot based on the actual area that you have here, because this is always reported, an engineering standpoint, it's always reported based on what was the area to begin with. Nobody comes in a regular test and figure out exactly what is the section in that neck. If they did, you'll get something like this. And we can do that reconstruction using these equations here, and it's covered in most books, where you change from the nominal elongation to the net elongation by using the actual area, and same for stress. You take the load divided by the actual area as opposed to the area that you begin with. So metals harden, especially at ambient temperature. And it becomes a difficulty explaining to some people. They think, especially with the age of fine element analysis, you run a fine element analysis, you get 15% deformation. Oh, maybe it's breaking. Well, it depends. If you don't have tension, no, it's not breaking. It's only the tension part. It's this instability that makes the tensile elongation. There's no relevance with respect to the intrinsic deformation of the material. The reason I bring it up, so this is just saying it will keep hardening, and the rate is going down. And that general law, the power hardening law, is a good way to curve fit a lot of metal behavior. The polymers doesn't really work, but with respect to the metals, this general way of taking a log plot, taking the slope, you get your strain hardening exponent essentially, and it's very useful. The way eventually your hardening becomes low at ambient temperature. I think it's good for you guys to have an idea. When you reach 200 or 300% strain in steel, for example, you have so much going on. It's filled with dislocation that even if it's ambient temperature, there will be recovery. There will be recombination of the defect. So eventually this curve will saturate. But it's at very high deformation value. It's involving essentially a lot of strain and very, very high stress. You're likely to crack depending on your exact working condition. If you try to do these very, very high, if you try to reach a steady flow stress, and that we're going to see in hot forming. This is just the written representation of what I was talking about here, where at the beginning in this curve, if I'm starting to deform at point A, the elongation is the same along the whole elevation. The gauge length is in this direction. I get to point B, it's still the same. At point C, I'm still the same, but then I form the neck. So if in this case in the middle, that's where the deformation localizes. So your strain is starting to go up here, and you're done deforming outside the neck. And that also happens in polymer. Polymers will, if they're ductile, they will form the neck. With the difference, the neck will also stabilize, and then you propagate the neck up and down to reach the full deformation height. And we'll talk about polymer at a slightly different time. So I don't have that specimen here. I was looking for it this morning, but what happens with a round specimen, and I'll draw it here. It's about the best way to do it. With a round specimen, say if I pull on it, I got it machined, and everything is going on very nicely at the beginning. It's all deforming homogeneously, so it stretches to say this. We're at 20% elongation. We started here with our gauge length, we're at 20% elongation, and then we start forming that neck. So it's reduced in area here, and when you look at it on a plane, eventually it will snap. And typically, you know, you can get to a local area that's about half of what you started with as the nominal area, exactly where the crack propagate. And the way the crack will propagate, if I look a little bit more at an angle here at this sample, it will look what we call a cone and cup. So you'll have this essentially going perpendicular here. So this is where it started. It will normally snap somewhere in the middle because you get more tension there with the stress concentration as you're forming the neck. And then when you get close to the edge, this will tend to be at 45 degrees. So if I do on a side view, it will look like this. One side is going to be like this, and then you have your neck. So this is the shear fracture here, and the matching face will be like this. So, all right. So this used to connect to here, and that was our neck. And now what we've introduced is a transverse crack and then these shear lips. The reason I mentioned that is I wanted to show you what happens when you put pressure. Now we're looking at actual sample, and you can see initially, if you do it just in the lab at atmospheric pressure, you get this zone here to be fairly big. So we're looking at this flat portion here at ambient temperature. And the flat portion, if you keep going to this image, this image, this image, this image, all the way here, there's almost none. So this sample here at the extreme is just looking as a 45 degree here with our little fillet like here. What does that mean? It means if we're going to deform the material at very high strain and avoid forming little cracks in it, we try to be in compression. It's one of the main reasons, especially if you're going to very high strain, it's the main reason for doing everything in compression. So rolling, extrusion, forging, you name it. You try to make sure you don't have areas that are going to deform in tension. In forging, it can be a problem. So when you're making that head, this is made with a round bar, and a lot of times it's cold form to make the exact shape, and it will even include the stamping on it. Most of the times there are multiple forging operations to lead to the final geometry, and the reason is if you try to do it all at once, you'll get tension somewhere. So you have to go progressively. And I can circulate that around. It has a galvanizing on it. It's one of those projects where I did a failure analysis, and it didn't fail through any of this. It didn't neck. It failed as a very straight cut. Yes?
What happens if you have a rod or something that doesn't have a circular cross-section?
We'll get to that. Yes, I have a video to illustrate that. It's a very good question. So essentially, the piece you're looking at, I cut it in 3 pieces. So you got the first part, this goes on, and then you have the tread, and it failed at the tread without any necking. And that's something that we talk about more in the second half module of the class. So in terms of how we do this deformation, forging is that example here with the head. Rolling is what I'm going to talk about, and most of the time to do beams, you do a form of rolling, and I have a little video to show to you on that. Wires, you can draw. Drawing has advantages where you can control the dimensions very precisely. At the same time, there's only so much you can pull. So you can pull and push. There are a lot of things you have to do to make sure you get exactly what you want. Extrusion is common for metals and polymer. It's used a lot for aluminum. These were extruded, and I'll talk about that separately. Deep drawing is how you make the aluminum cans for soda and stuff. So you start with a flat and you essentially put it between a die and a punch to extrude it, and that's why the wall is so thin, because it gets stretched. So the deep drawing is one example where there is tension during deformation, and you have to be very careful in terms of what the material hardening is. The advantage of aluminum is you can tailor it so it will harden quite a bit, and you want that. So you wouldn't try to do deep drawing at high temperature. It will just break on you. You need the hardening to do it. Stretch forming is used a lot for fuselage. So you take the sheets and you put it on a complex surface, a double curvature surface. It's the reason for doing it that way. You deform it plastically and you get some spring back, but not a whole lot, because you really went and plasticized the whole thickness of the plate. And then you can put some holes, or you put the holes before to rivet everything together and make the fuselage. The other one's just more of a forming operation, as opposed to, the bending is used a lot for making products. You can make door frames that everything is bent. Shelves, there's a lot of bending. It's straightened the components to have bends everywhere on the edges. And that's an advantage of metals. You can just do it at ambient temperature, forming these 90-degree bends. No need to eat it. So I wanted to show you a brief video.
Steel is highly resistant to shaping when it's cold, and for that reason it is generally rolled whilst it's hot.
So you don't feel the heat right now, but it's hot, and what happens is they explain here that you preheat the metal before you start deforming, and then a lot of processes, at least the traditional processes from there, will be autogenous. So you wouldn't try to keep heating the metal. By the deformation, it reheats itself. That's how you make the beams in the different shapes.
Forces of tens of millions of newtons, equivalent to a weight of thousands of tons. The rolls, therefore, run in massive bearings, mounted in housings of enormous strength and driven by powerful electric motors. These are known as mill stands. The layout of a rolling mill can vary from...
So one thing that I want to point out here, and it's used a lot, the rolling design is definitely not something we need to get into, but you have to think about the radius of your roll is going to affect how much reduction you can take at each pass. So that's why they have different roll diameter. And another key aspect I want to introduce to you is, as you keep reducing the section, you have to go faster, because now you have more surfaces as opposed to volume, and therefore you're extracting the same heat through radiation, but you need to produce more. So these processes typically start, you get the big piece, and you start moving it slowly and maintain the temperature essentially. And as you keep reducing the section, all of a sudden it starts flying around. When I was talking about the springs for suspensions, when you get to the smaller diameter, it flies around. It's very high speed. What else can I say about this? You can do a lot of shapes. You have to be obviously putting a lot of capital investment. Making these rolling mills is very expensive. And that's why the beam I circulated around was not made by any of this high temperature deformation processing. They had 3 plates, and it was, in this case, laser welded together. It's more of a prototype. In reality, what happens in custom fabrication is people will use, instead of laser welding, you have submerged arc welding that allows you to make a very big weld in one pass. So there are, in construction site, portable unit that you take the plates and you make any beam you want from it. It's not as good quality as rolling it, but you can definitely get your custom shapes, and you don't need as many different material supply. So it'd be applicable if you have a situation, each piece is not reproduced in that much volume, so you're better off just buy the stock plate and make your beams. It introduces deformation from the cooling of the well and all sorts of other issues, but in some cases it works. So there's no reason to make it more expensive or complicated. So in the rolling, I mentioned the size of the roller matters, how much friction you get, because the power for moving the metal is provided by the rollers. It sometimes needs to be a very, very strong motor. And one of the criteria is you want to make sure, so if you have your contact here and you start at an angle alpha between this point of contact and the center line, so this is the main angle here, you want to be able to, by the friction, to get the metal engaged between your rolls. So there's this critical angle, and this is something that comes up a lot in engineering projects where people worry about friction, and it's actually simpler than we can think. So if I have the engagement here with the metal, and then I deform it, it comes out this way. So what we're interested, and I put a symmetry plane here. What we're interested is make sure that here we have our normal force going this way, and then we have our friction force. Let's put it, yeah, it doesn't matter. So we want to make sure that our friction over our normal force is essentially in the same ratio of the angle here. So it's the tangent, it's the opposite angle to the close angle, and that's your friction coefficient here. So it's not specific to this rolling process. It's something that comes up with blowout preventers. It comes up with a lot of applications where people say, well, you know, is this going to slide or not? Well, that's all you need. That's all you need to figure out, your attack angle. And from there, you get deformation going through a very small amount at the beginning, and from at point A here, or somewhere in the middle, you reach the highest amount of reduction in section for a given period of time. So that's going to be your hot zone as the process goes on. And you try to make sure in that zone you don't become too hot, so you have a lot of grain growth or other things like that. So you have to make sure that between the very hot zone and the surface, everything is at a temperature, a good working temperature. So that's another limiting factor when you try to design the rolling process. You're looking at high temperature. So we say in general creep, so slow deformation, happens above half of the melting point if you take the melting point in Kelvin. So for hot working, you want to be above that threshold. So put here as 0.6. It's a rule of thumb. It's not exact, but it's a temperature where you get a fair amount of recovery in your material. The strain rate starts at 0.5. So that was not completed. When I say 0.5, it's essentially, so 0.5 inch per second. It's fast. So 50% per second is kind of a lower bound for these deformation processes. That's why you see things moving around. Now, it starts a little slower. And the reason is you don't want to heat too much your workpiece when it's big. And as you keep going on, it keeps going faster. The hot working is the way to go to homogenize the structure, get very high deformation ratio, start for something this big to a plate that's a 1/4 inch or less. The main drawback on this is it's hot, and then you may have seen in the video at the end, they spray the hot metal to cool it back to ambient temperature, because if you cool slowly the stainless steel, there are a lot of metals, you can get some brittle transformation. You can essentially sensitize stainless steel. There are a lot of reasons for not cooling it in the slowest possible way. What it means in practice is you don't have the wall thickness tolerance out of a hot roll sheet that you get out of a cold roll sheet. The cold roll is really, you deform it, you let it go off the roll, and that's it. Nothing else happens. So you get a better dimensional control over cold worked sheets as opposed to hot roll sheets. And it doesn't mean that, I say the cold roll would be higher yield strength, obviously because you have the strain hardening, but you can anneal those at relatively low temperature and still have the better dimensional tolerance. So when you see, if you happen to be involved in any kind of, oh yeah, let's buy a little piece of this, a little piece of that, that's the reason why even in McMaster they'll tell you if this is a hot roll product, a cold roll, regardless of what the yield strength specification is, because it's affecting your dimensional tolerance. This is useful just as an introduction to the mechanical metallurgy that I want to introduce to you. Is you try to work the metal at a temperature that's sufficient that your flow stress, and that's this y-axis here, over the strain just becomes the same. So you just keep deforming it, it's fine, nothing changed. You don't have to increase the force on your rolls, it's just going to keep going and you can keep deforming it. It's usual to have a reduction in net area of 100. It's kind of a rule of thumb, and you can have more than that between your starting material and your final product. So I have these tubes here, and that's a project that I've been working on for a medical device. What happened is they want to use this as a double layer where you supply a liquid into the inner tube. It gets to the end and it's pressurized here, and when it is exiting from these little holes, the pressure is going down and becomes a gas. It's cooling down, and they use that to make ablation on the heart. So you put it in, and then when you have it positioned exactly, say you want to bend it right exactly like this, the surgeon says, okay, so they start cooling. It goes to below 100 degrees centigrade,